How's it going, everybody? In this video, we're going to take a slight break from the SD-WAN focus, and we're going to be getting the ASA up and running to provide internet access to our HQ site. So we're going to get ASA 1 up and running and squared away, and then we're going to make sure that switch 16 is good to go with that. You might notice a slight modification in the topology. I did eliminate the connection between switch 17 and ASA 1. Because switch 17 is being used strictly for layer 2 connectivity between the V edges and iOS 5 and 6, where switch 16 is actually going to be providing routed connectivity for internet connectivity as well as iOS 5 to the rest of the environment. So we have like a back-end connection to the rest of the network. So with that being said, what we're going to focus on is getting the ASA up and running. So we'll bootstrap the ASA. And then we're going to go through, get him squared away, and then running Ospf to propagate a default route to switch 16. Once we have that in play, we'll be in good shape. That shouldn't take us very long at all, to be honest with you, but that's basically what we're going to do. We get that working, and then in the next videos, the next video, we're going to focus on just a high-level understanding of Ospf. So for those of you that don't know Ospf that well. So let me go ahead and get out of the way. So here on the ASA, as you can see, it's a blank configuration. If I do a show interface IP brief, there's nothing configured. So the first thing we have to do is go ahead and set a host name. So it's going to be host name is going to be ASA1. And then we're going to, let me scoot this over just a little bit so we can see the interface configs. So I'm going to set up the interface configs. So interface gig0/2. Will be IP address of 192.1.101.2 and then a /24 mask. I'm going to no shut that port and give it a nameif of outside. And then I'm going to go to interface gig0/0. IP address here is going to be 10.1.160.1/24. I'm going to no shut this guy and nameif of inside _ switch 16. And then we're going to set the security level on this one to be 100. So we have that high level security zone to low level security zone flow from inside to outside. So now that we've got that squared away, the next thing for me to go do is get the default route in play. So if we do a show route, we don't have a default route. So we're going to type in route outside 00 for our default route and then 192.1.101.1. Something fairly simple like that. Now the next step for us to go through and do is to get Ospf running for this particular network. So I'm going to type in router Ospf1 and then network of 10.1.160.0/24 mask and then area 0. We'll give that a couple of seconds and that should come up pretty quickly on switch 16, which it's there. Awesome. Now if we check on switch 16 and we look at the routing table, show IP route, right now, we're not learning anything, right? If we go back to the ASA, bring this down just a little bit. If we look at the ASA, we do a show route. We are learning some Ospf routes. And you notice that there's a static route in the routing table. If we look back at switch 16, we do a show run. I'm sorry, no, that is the static route that I created. Never mind, my fault. What I need to do is I need to take this static route right here and I need to propagate it to the switch in order for it to propagate that to the V edges. So what I'm going to do on the ASA is I'm going to type in default information originate. And basically what this command does in a nutshell is it will automatically generate a default route into Ospf to all the devices in the Ospf domain, as long as there's actually a static route or a default route, I should say, in the routing table. So as long as this route here is in the routing table, then we'll be in good shape. Then we'll be able to go through and to propagate that route. If we come back over here and do a show IP route, you can see that there's an Ospf default route in the routing table, which is what we want to have. So that's basically how that comes into play. Not much more to it than that. The last step for me to go do, now that we have the routing in place, is to go back to the ASA and I need to set up NAT. So underneath here, I'm going to type in object network, and I'm going to call this internal LANs, and I'm going to type in the subnet of 10.0.0.0/8. And the reason why I'm going to choose that is because I have a lot of connectivity from pretty much all of my sites are 10 something, and I've used that that setup, so LAN segments will be able to communicate out to the internet. So I'm going to type that in, and then I'm going to specify NAT, and I'm going to do a auto NAT. So I'm going to come in here and type in, or also what they refer to as an object NAT. So I'll type in inside switch 16 to outside, dynamic connection, so basically port address translation or dynamic PAT to the interface of G0/2. Okay, so that's my NAT configuration. So I do a show run. I have my interface configured, and I have my NAT statement good to go. Everything's looking pretty good. So if we do a show run NAT, my NAT config is there. If we do a show run object network, there we go. And so in other words, if I was to go to switch 16 and ping, in this case here, inet1 has an IP address on it, show IP interface brief of 1234. So if I ping 1.2.3.4, actually let me do it this way. Let me do a repeat of 100. So I'm testing this on purpose the way that I am. So the ASA by default is going to block ping. So let me do a show run policy map and go to global config, and underneath here we'll go ahead and inspect in the icmp. Okay, so now if I go back to switch 16, the pings should start to work. Now the pings are starting to work now, which is great. Now if I do a trace route to 1.2.3.4 numerically, trace route 1.2.3.4, yes, numeric display, and then just at the end. So what's going to end up happening is it won't get anywhere. And the reason why is a couple of things. The first one is that the ASA will not decrement the TTL, or the time to live field. So what it does is it won't decrement TTL. So it won't look into the TTL portion of the IP header and pull the TTL value down, because as traffic is passing through it. And it also doesn't allow the response of trace route, time exceeded and unreachables to come back. So that's something we have to actually go in here and adjust. So I'm going to go on the ASA, and how I do this is show run policy -map again. We go to global config, we go underneath the global policy map, and then underneath the class-default, we type in the command set for connections. We say decrement-ttl. That's the first step. Then we go back to switch 16. We'll go ahead and we'll cancel this. And then after we get this config, we'll be in good shape. That's the first step we need to make. The second step we need to make is configure an ACL. So it'll be access list, and then we're going to call this outside in, and then we're going to say extended, and we're going to say permit, and I'm going to say icmp, or sorry, not icmp. Permit from any source for permit. Oh, that's right. It's going to be IP any, and then I'm sorry. No, that's not right. No, it's icmp. icmp from any source to any destination, as long as it. There we go. Here's what I was looking for. As long as it's either a time exceeded or a any, or as long as it's an unreachable. And I'll throw in trace route as well for this, is just for good measure. Now that we got the ACL created, we need to apply it. So we'll type in access-group outside, make sure I type it in right, in interface outside. What that basically will do now, if we do a show access group the access list. If we go to send any traffic now, that ping, do that ping again, right? The ping is allowed to go through, right? But that has nothing to do with the trace route. If we do the trace route again, the 1.2.3.4, and we specify numeric, and we do this, now the ASA should show up in the output, which it does. So it gets where it's got to go. We see 10.1.160.1, which happens to be the gig 00 interface of the ASA. And then it also, when the trace route went out, it sent basically an icmp ping, and then when the response came back in, it came in with an time exceeded and an unreachable message back in, and that's what allows the trace route to appear. So yeah, it does work all day long, and it gets the job done. So now if I was to do a trace route from anywhere else, we're going to get the same output. Alright, so now that we've got that squared away, we're in good shape because now we'll be able to do that. Would I normally do this in a production environment? Absolutely not. But I'm doing it just to help represent that the traffic is actually flowing the way that it needs to. I have done this to demonstrate to customers that it will work, because some people don't realize this when they work with an ASA firewall, that this stuff does come into play and is needed to be understood. But beyond this, that's pretty much what you need to know about getting all this stuff up and running. But for lab purposes, I was like, this would be kind of cool for people to see, instead of me just saying it's working and then people see the stars show up. That doesn't really prove my point. So, at any rate, I hope you guys enjoyed this. Until next time, guys, take it easy.